Good afternoon. Welcome you to our final part of N-slit diffraction. Okay, after completing single slit and double slit, in the last class we had seen the first part of N-slit diffraction, and today we are going to see the next part. Okay, so reminding all of you, what are the points that we have already discussed in the last class regarding N-slits? We have found out the path difference, then the phase difference caused due to these N-slit diffraction. Then we have calculated the resultant amplitude on the screen, and then we have also seen the intensity caused due to N-slits on the screen. And then we had also seen the condition for central maxima as such. Now, please just let us take a small recap of the last part that we have already done, because that is very, very important. We had calculated that the intensity due to n number of slits is given by A0 square sine square alpha by alpha square sine square n beta by sine square beta. This is the so-called equation for n-slit diffraction intensity. While we are writing this, we will always remember to write down what is this alpha. This alpha, reminding all of you, is pi by lambda a sine theta, whereas this beta is the angle pi by lambda a plus b sine theta, where a is the slit width and b is the slit separation. Alright, so this particular equation is the intensity caused due to the diffraction occurring at n slits. Okay, then we had found out the condition for central maxima to be something like this, that sine beta. Sine beta was taken to be 0, and then we had calculated that value to be plus minus n pi. Now, students, it would be actually good that I tell you that we should be calling these maximas, this condition for, instead of central maxima, actually, I should have told you that this is the condition for principal maxima. All right. So please note that this should actually be called as principal maxima. And why so? Sorry, principal maxima. And the particular condition where this m value is 0, that exact only that should be called as the central maxima. Okay, as I was going through the material yesterday, I found that it is good that we call all these maximas occurring at these conditions to be the principal maxima, whereas the one which is just at the center, where the value of this m over here is 0, we will call that particular only that maxima as the central maxima. So if I write a plus b sine theta is equal to plus minus m lambda, these values, these condition actually is that for principal maximas. However, among all those principal maximas, when I consider only the value of m is equal to 0, I may call that. Alright, so these were the things that we had discussed. After discussing this, remember, we had also calculated that what can be the maximum intensity, which means what is the intensity at the central maxima. And what was that, or the principal maxima as such, if I may call so. And we had calculated that was equal to n square a0 square sine square alpha by alpha square. Now, if you just go back to your double slit, remember what was the maximum intensity of the central maxima there? It was 4 into a0 square sine square alpha by alpha square. So as if it was n is equal to 2, slit number is equal to 2, and when we were squaring it, we were getting a 4 over there. So even this particular maximum intensity formula is also directly proportional to what? Directly proportional to n square. If I keep n is equal to 1, it is a0 square sine square alpha by alpha square, which is the maximum intensity possible for single slit. When we are going to double slit, it becomes 4 times. And like this, as we are going on increasing our n, or the number of slits, this maximum intensity varies as the square of that particular number. Alright, so up to here we have already discussed. Now it is time for us to move forward to see the next conditions. So as the next condition, what we will be considering is the condition for minimas now. Alright, so next thing that we are going to discuss would be the conditions for minima. Acha, one more thing I would like to remind all of you over here, or rather show you over here, that when we have calculated this, this is the so-called intensity of n-slit diffraction pattern. You will see that yesterday when I was doing the principal maxima conditions, I have actually worked with only this term, isn't it? I have not worked with this alpha term. I have directly worked with this beta term. Now, actually, the reason behind this is when our diffraction is occurring at n number of slits, large number of slits, it is seen that the second term, the term regarding the relating to the beta thing, actually is more, what to say, it has its effect which is more pronounced. All right, so it is not the sine square alpha by alpha square term which is more powerful in this case, rather it is this term which is more powerful, and hence for calculating the maximas and minimas for n slit, it is this sine square n beta by sine square beta term that actually is considered, okay, and is given more importance. It is actually coming from the observation. All right, so today when we are finding out the condition for minimas, once again, what are we going to, where are we going to put our interest? We are going to put our interest again on this sine square n beta by sine square beta. Now, what do we know about the intensity at the minima? Intensity at the minima has to be 0, right? So in this scenario, among this, within this quantity, the denominator obviously cannot be put to 0. So obviously the numerator has to be 0, which means sine n beta must be 0, and this must give us the condition for getting the minima or the intensity minimas, right? So if sine n beta is equal to 0, once again we might be getting the condition that this is plus minus some n pi. I have very knowingly not written this as m pi because remember we had used the term m for getting the principal maximus. So that we can differentiate between these numbers, we are writing it with a small n in this case. All right. Now, what can be the values in this case? What can be, or rather I would say that n beta is equal to plus minus n lambda. Correct. So let me just strike it off. So this is where we are standing. Now reminding all of you, what is this beta? This beta is, this beta, if you remember, as we were defining it, it was a plus b sine theta. This is equal to plus minus n pi. So if we cancel out these pi's and if I take this n by lambda to the right hand side, what will I be getting? I will be getting this condition as lambda by n. So actually this is the condition for getting the minimas. But students, here this discussion will not be complete until we talk about the values of this n. So what can be the values of n? Now remember, whenever a plus b sine beta is equal to 0 or 1 or 2, what are those conditions? A plus b sine theta is equal to 0, plus minus 1, plus minus 2 were the conditions of principal maxima, isn't it? So in this scenario, when I am going to define this small n, remember this n cannot be equal to 0, right? So n cannot be equal to 0. However, n can be anything from 1, 2, 3 and so on. Right? So remember, while we are discussing or while we are defining this n over here, this n will not be equal to 0 because n is equal to 0 is the condition for my central maxima. A plus b sine theta is equal to 0 is the condition for my central maxima. Fine. Now, while I am writing down the value of n as 1, 2, 3, again remember, look at the right hand side. I have the expression as small n by capital N. Now suppose that we are working with a particular diffraction grating, or say the number of slits in this case is say 3. Then what will happen if n is equal to, say, or n is equal to 5. So I am considering slit is equal to 5. So what will happen if this n is also 5 and this is also 5? What will I get? My condition will become a plus b sine theta is equal to plus minus lambda. Once again, remember, a plus b sine theta is equal to plus minus lambda is the condition for the first order primary maxima, isn't it? A plus b sine theta is equal to 0 is the condition for central maxima. A plus B sin theta is equal to plus minus lambda is the condition for first order primary maxima. So in this case, when we are considering this, if I write it down once again, this small n cannot be equal to the value of the slit numbers as well. So in this case, n cannot be n. So since we were considering or we were talking about n is equal to 5, so what will be my allowed values? N is equal to 1, 2, 3 and 4, but I will not have the value of 5 over here because n is equal to 5 will give me the condition for getting my first order primary maxima. Alright, now moving forward, so I cannot have n, but what can I have? I can again have 6, I can have 7, I can have 8, I can have 9, but what about n is equal to 10? The moment I will be putting 10, since my 5, this n is equal to 5 and I have put over here as 10, what will I be left with? I will be left with plus minus 2 lambda. Now remember, a plus b sin theta is equal to plus minus 2 lambda is the condition for getting second order primary maxima. So once again, what we will miss? We will miss the order n is equal to 10. Alright, we will not be allowed to have the n is equal to 10 value. Like this, if we write a generalized formula, if I write a generalized thing, n by capital N into lambda. So what are the values of this n? N can be 1, 2 till n minus 1. N value is not allowed. What are the not allowed values? The not allowed values is 0, n, 2n, 3n and so on. Whereas allowed values are n plus 1. Then like this we can go on. Again we will not be having have it only till 2n minus 1. 2n will not be allowed. And again we can have as 2n plus 1 and so on. Alright. So among all the values of this number n, 0 is not allowed. N is not allowed. Twice n is not allowed. Thrice n is not allowed. But the remaining numbers are allowed. So these are the so-called conditions or the numbers which are allowed to get the conditions for minima. Alright, I hope everything is clear now that when we are calculating or when we are talking about the minimas available on the screen, these values cannot be or are not allowed. However, the rest of them are allowed. Alright, so is this clear to all of us? Now what we are actually going towards is the condition for secondary maximas. Okay, so let us move forward to our secondary maximas. Now, students, this part that we are now actually going to do is a bit tedious. Okay, this is a disclaimer. This is going to be a little boring because we have to do a lot of mathematics. The steps will be very, very easy, but it will be long. It will be a little tedious. However, because it is very important, so I hope all of you will be taking care to understand each of the individual steps. All right. So moving forward, I am going to now tell you about the conditions for secondary maxima. All right. So we are now going to talk about the secondary maxima. Once again, from where am I going to get this? We will again go back to the intensity of n slits, which is a0 square sine square alpha by alpha square sine square n beta by sine square beta. And what am I trying to find out? I am trying to find out the maxima, the secondary maxima conditions from this very expression. So from where are we going to find this out? Reminding all of you, as I was telling you a little ago as well, that in case of n number of slits, this term a0 square or the alpha term actually is not that important in contribution. More contribution comes from the sine square n beta by sine square beta term. All right, I have missed a square over here. So this is more important. So if I have to now find out the condition for getting the secondary maximas, what I can do is I can differentiate this intensity with respect to beta. All right. What we are going to do, see, beta term is more important and that is the reason why we are going to differentiate this intensity with respect to beta and then we will equate it to 0. The same method in which we find out generally the minima and the maxima conditions. So this is what we are going to do now. Okay. However, see, if I am doing the differentiation with respect to beta only, this a0 square sine square alpha by alpha square is independent of beta. So what am I actually doing? I am actually going to do, I'll keep these terms out and I can just do the calculation of this part, which is sine n beta by sine beta whole square. Isn't it? This is what we have to do, and do not forget that we have to equate this entire thing as 0 since we need to find out the maxima condition. Alright, so now let us move forward. So what we are going to do, we are going to solve for this part. So what do I have? I have 0 is equal to, this part remains unaltered, sine square alpha by alpha square. So see, what am I doing? I am differentiating the term sine n beta by sine beta whole square. So what will I have? dd beta of something squared. So I will be having this as 2 of sine n beta by sine beta. However, now I must differentiate this quantity, which is sine n beta by sine beta. Correct? So this is what is our next step. So moving forward, when I have to differentiate this term sine n beta by sine beta, this is like differentiating something like a quantity which is having a numerator and a denominator. So we will use our formula like that. So if I keep this as 0 is equal to this part as common, let me write it down anyway. Sine square alpha by alpha square 2 of sine n beta by sine beta. What am I doing now? I am going to differentiate this. So what am I going to have? Numerator square, denominator square, sine square beta, denominator sine beta, dd beta of numerator, which means differentiation of sine and beta. Sine and beta, if I differentiate, I will have n cos n beta, correct? Minus, let me take this little common. See, I have a sine square beta here. Students, I hope all of you have understood that I have a sine beta here and I have a sine square beta here. Because of the lack of space, I am just taking this sine square over here. Okay, so as a result, what am I having? I am having sine beta n cos n beta minus, now who will remain silent? N sine n beta will remain silent. dd beta of sine beta is cos beta. I hope all of you have followed the step. All I have done is I have just differentiated the quantity sine and beta by sine beta. And we have received this type of a huge looking quantity. Now, left hand side obviously is equal to 0. Now students, please try to understand the significance of this particular equation. I have something, this entire right hand side is equal to 0. However, it is a product of many terms. And what are they? A0 square sine square alpha by alpha square. Now see, if in this entire right hand side A0 square is 0, my entire right hand side will become 0. So it has no significance. If sine square alpha by alpha square becomes 0, once again, it has no meaning. Similarly, this condition can also not be equal to 0. We have already seen that if sine and beta is equal to 0, that gives us the condition for minimas. If sine beta is equal to 0, that gives us the condition for primary maximas. So, none of these quantities can be 0. Only which part can be 0? This part within the brackets is allowed to be 0. So, can I not write then that sine n beta, let me write it little bit properly. Sine beta into n cos n beta minus sine n beta cos beta is equal to 0. So this is where we are left. Reminding all of you, why did we make this quantity 0? Because the rest of the terms or rest of the things that we were having, if they were 0, either the entire term was going to 0 or they were giving us the separate conditions. Either sine n beta 0 was the condition for minimas, sine beta equal to 0 was the condition for primary maximas. And since we are now trying to find out the condition for secondary maximas, only this quantity is equal to 0 is allowed for us. Now, if this is possible, if this is true, I hope we can write this as sine beta into n into cos n beta is equal to sine n beta cos beta. Fine. So now let us bring the like terms together. So what do I have? I will bring this sine beta and cos beta together, and I will take this cos n beta to the right hand side. So what do I have in my left hand side? This n remains like this. Sine beta, cos beta comes as a denominator here. This is equal to sine n beta, and I will take this cos beta as a denominator there. Now, dear students, is this picture more clear now? So, what are we actually having? We are now having our condition for secondary maximas. N tan beta is equal to tan n beta. This is the so-called condition that we have been trying to find out. Okay, now obviously you all will be asking me in the second question is, what are the allowed values of beta for which this condition will hold, and so that secondary maxima conditions can be found out, or the values of beta can be found out. Now see, if you remember how we had solved the first order, I mean the single slit, we had calculated, we had separately drawn alpha, we had separately drawn tan alpha, we had found out their intersection points, and then we had calculated the individual thing. The same thing can be done in this scenario as well. However, we need not do that. Please listen what I told. We need not do the next calculations to find out the values of individual betas. And why so? Two reasons. The first reason being very practical, this is not required for us from the point of view of our examination or from the point of view of any given examination as such. However, the second reason is that why we are not so much interested to know the conditions for getting the exact values of beta is actually that the intensity of the secondary maximas when compared to the principal maximas is very, very less. So less that eventually, generally when we do the experiments, if n is very large, if the number of slits is very large, the secondary maximas are not even seen. And because of that, if something I cannot see, will I be interested to find that more about it? But now you may ask me that, ma'am, why will I believe that the intensity is very low? Intensity of the secondary maxima is very low. This is what I will now show you. So students, please remember, what am I asking you to do and what am I asking you to may not do? What is that? You can write down this particular equation as the condition for secondary maximas. This is enough. I am not asking you to find out the individual values of beta explicitly by plotting or by doing any kind of calculation. However, what should be kept in mind? It should be kept in mind that when I am finding out the conditions for secondary maximas, even in this scenario, remember beta is equal to plus minus m pi. These were the conditions for getting our principal maximus. So these values are excluded. Among all the allowed values of beta that someone can calculate, or I may calculate, or you may calculate, beta is equal to plus minus m pi, where m is equal to 0, 1, 2. These values are not allowed. Rest, whatever is coming, we are fine with it, and that is all we need to know about their condition. And now what I am asking you to show, or what I will be showing you now, will be what is the value of the intensity caused by a secondary maximum. And when you will see the value of this, you will realize that the value of this intensity of the secondary maximas is so insignificant that the secondary maxima condition also becomes a little bit not that important for us, and hence we are not doing later calculations. Okay, so what is my next step now? I want to show you the intensity due to secondary maximas on the screen. Alright, so now let's move forward. Now, I will keep this particular condition here. The rest of the things we can now just rub away. However, since I am going to calculate the intensity, it will be apt that I also keep the intensity due to Slits expression. I will keep it here for our future reference. Sine square alpha by alpha square, sine square n beta by sine square beta. Let this be there, visible to us. Now we are going to begin from this very expression. Actually, let me tell you why did I write this? Why did I write this? See, I need to actually show you the significance of this term. If I can find out the value of this sine square n beta by sine square beta, and I can put it over here under the conditions of secondary maxima, under the condition that n tan beta is equal to tan n beta, I will be getting the intensity for n slits at the secondary maximas. So starting from this condition, we will now find out the value of this term within the brackets or the beta term. Okay. So this is what I am trying to do. Now look into this equation. Tan n beta, tan of some angle is given by n tan beta. What I am writing it as is n tan beta by 1. Why did I take this particular step? Why did I write this by 1? See, remember, tangent, what is the value of tan theta? What do you mean by tan theta? Tan theta means that suppose there is a right angled triangle. If this angle is n beta, I hope you can see yes. If this angle is n beta, what is this? Tangent of any value is the opposite by the base, isn't it? We generally write any angle as tangent of that angle is equal to the opposite of this triangle and the base of this triangle, isn't it? Now, since tan n beta is n tan beta by 1, isn't this showing me that the value of this part of this triangle is n tan beta, whereas the value of this base is unity, is 1. Are you following me? So, by using this pictorial representation, what I can now find out is if my base is 1 and if my opposite is n tan beta, what will be the value of the hypotenuse? The value of the hypotenuse, you all will agree with me, the hypotenuse will be, this will be under root 1 square plus n square tan square beta. Correct? This will be my hypotenuse. But why do I need the hypotenuse? Because remember, my goal is to actually find out this sine square n beta. I want to actually find out what is sine n beta. So, what will be the value of sine n beta? If tan n beta is this, sine n beta will be, what is sine n beta? Hypotenuse by opposite, opposite by hypotenuse. So, I can write it as sine n beta is equal to n tan beta by root over 1 square plus n square tan square beta. I hope you all are okay with this part, right? See, telling once again, this mathematics might be a little tedious, might be boring, but please be with me. Please patiently do this so that you will be getting a very, very nice result at the end. So, this is the scenario. But in my expression of intensity, I do not have a sine n beta. I have a sine square n beta. So, let us find out the value of sine square. If I have to calculate the value of sine square, I'll have to square the right hand side as well. So, what will I have? N square tan square beta. Squaring will get rid of the root for us. And I will be having this. Correct? However, in my expression of intensity, it is not only sine square n beta which is there. One more quantity is there, which is that sine square n beta by sine square beta, which means I have to now calculate what will be the value of this by sine square beta, which means I can simply write this as 1 by sine square beta. Students, is this okay? Move forward. Let me just, shall I move this? We can once again write later on. So this is where we are now standing. Now, little bit more of mathematics, little bit more, okay? What will I do? I will write this tan square as n square sine square beta by cos square beta. Students, please bear with me. I hope you all will be very happy finally when you get the answer. Here also I have a 1 square plus n square tan square beta by cos square beta into sine square beta. Okay, now let me take the LCM, which means I will take this LCM over here. So I hope all of you will agree that if I write this as cos square beta, what was that? O plus. Did I have a plus here or yes, I had a plus here. Okay, so see, let me write it little clearly then. I have a cos square beta plus n square sine square beta by cos square beta. This. So now look into the expression little carefully. This sine square beta is getting cancelled with this sine square beta. This cos square beta is getting cancelled with this cos square beta. So finally, what am I left with? The value of sine square n beta by sine square beta is coming out to be only n square by this cos square beta plus n square sine square beta. We are almost done. We have almost done the entire boring mathematics. Finally, since I do not want to have a cos here, let me convert this cos square beta as 1 minus sine square beta. Where am I writing square? Did I, is it okay now? Sometimes there may be, because I'm jumbling up a lot of things, one square or the other might be looking as if I have put it. So over here, this is the condition. So what did I tell you? That I am going to put the value of this cos square beta as 1 minus sine square beta. So this is what is left with me. Now please look into this expression. I have two terms with sine square beta. One has the coefficient n square, the other has the coefficient of minus 1. So can I not write this as n square 1 plus, which means if I take a common of sine square beta, it is n square minus 1. So finally, now that I have this particular expression for my sine square n beta by sine square beta, which is this. So when I take this particular value, if I take this particular value to my intensity distribution, what can I write? I can write the value of the secondary maxima, the intensity at secondary maxima as A0 square sine square alpha by alpha square n square 1 plus n square minus 1 sine square beta. Is it okay? Is it okay with all of you? So this is the intensity due to a secondary maxima on the screen. However, reminding you what was the intensity of the central maxima, remember? Or the principal maxima? The principal maxima, let me write it down as, it was A0 square sine square alpha by alpha square into n square. Correct? So if I ask you what is the ratio of the intensities, if I want to know intensity due to secondary maxima and intensity due to primary maxima, what will be my value? This entire quantity, a square n square sine square alpha by alpha square will be getting cancelled, and all I will be having left is 1 plus n square minus 1 sine square beta, or the intensity due to the secondary maxima is intensity of the central maxima or the principal maxima divided by this number. Fine. Now, as I was telling you, if I put this n is equal to something large, what will be the ratio of these two? The intensity of the secondary maxima will be so less that it can be almost, it will not be even visible to us. All right. Now, over here, let me take you all to the physics laboratory. I hope all of you will remember that all of you have done an experiment with diffraction grating. Remember where diffraction was occurring through large number of slits, where this n was large. If you remember the intensity spectrum that we see, what do we see? We see the central spot, then we see the second primary maxima, two primary the first order primary maxima on two sides, second order primary maximas on the two sides. However, do we see the secondary maximas at all? We cannot see the secondary maximas at all, because if this n is very large, see, this denominator is so big that this becomes the secondary maxima intensity becomes very, very small. All right. So basically, what is Shrestha asking? If you followed this, in between, if there was some, while writing, if there was some mistake, I guess we all will be able to understand that. Okay, so as I was telling you, what happens, the secondary maxima intensities when compared to the primary maximas is so low that they are hardly visible to us, and hence we are not that much interested to know at what values exactly of beta they are occurring, and hence I have not asked you to individually calculate that n tan beta is equal to tan n beta solution. Okay, so this is what is our intensity formula. But what I want to next show you is actually what will be the intensity distribution on the screen, which means what am I going to see. Okay, so let me just move forward in showing you the particular intensity distribution. We can call this as the intensity distribution as to how the intensity will be distributed over the screen. All right, so see, what have we seen? When I have calculated the value of sine square beta, n beta by sine square beta, with the help of this, we have calculated two things. By considering this, we have calculated the primary maximas, and we have also calculated the minimas. We have also calculated the secondary maximas. So actually, in case of n slit, the maxima and the minima conditions were given by this quantity, by the contribution from this quantity, and we have seen that it looks something like this. Say I have the central maxima, then I will have, say, the another primary maxima. See, let me give the names. This is my central maxima. This is my primary maxima order number 1 on the right side, primary maxima order number 1 on the left side. Like this, I will be having primary maxima order number 2, primary maxima order number 2 on both the sides and so on. However, in between these, remember, let me just write once again, AB sine theta is equal to plus minus m pi. These were the conditions for getting these primary maximas. M is equal to 0, 1, 2 and so on. However, for the same left hand side, A plus B sine theta is equal to plus minus n by n pi, we got the minimas. We got the minimas, and we also remembered that n was not equal to 0, n, 2n and so on. Students, I hope you have remembered these two conditions. From here, we are now trying to translate this information into a pictorial representation. What is that? Say now, let us consider the condition for n is equal to 5 slits. This n is equal to 5. Then can you tell me how many minimas will I have between the central maxima and the primary maxima 1? See, 0, n is equal to 0 is the secondary maxima. N is equal to n is my PM1. And in between 0 and n, in between 0 to 5, what are the allowed values of minima? 1, 2, 3 and 4. These values of n are only allowed to get my minima conditions, which means in between the central maxima and the primary maxima, I must be getting 4 values of minimas. See, this is one minima, this is another minima, and I should be having 2 more minimas in between these two from this condition only. So, if there are 4 minimas available, since minima condition is 0, these are the 0 values where I am pointing them. So, if there are these minima conditions, how will I reach from one minima to the other? I will reach there with the help of secondary maximas. Alright, so see here, while I have moved from the central maxima to the primary maxima number 1, I was allowed to have how many minima points? I was allowed to have 4 minima points. Minima point 1, minima point 2, minima point 3, minima point 4. Yes, Nana, very good. So these are my minima points. However, see, while I have drawn these 4 minima points, this figure is also showing me that how many secondary maximas will be allowed? 1, 2 and 3, which means if my slit number is 5, n minus 1 number of minimas will be there and n minus 2 number of secondary maximas will be there. Are you following me? Very good. Yes. So you all have understood this part. So this is what. But since I have drawn this on the right hand side, the same thing will be available to us on the left hand side as well. Like this. So again, from moving from the primary, this PM1 to PM2, I will have 3 more secondary maximas and so on. This will be completely moving forward along the entire screen. So this is the contribution from which part of our formula? From the sine square n beta by sine n beta. However, here what are we again having or having as well? We are also having the term sine square alpha by alpha square. Remember the contribution from individual slits? And how does that look like? If I keep the condition for central maxima at the same condition, remember again we will have a maxima. However, the secondary maxima will be much smaller. If this is I0, remember we had calculated that this will be I0 by 22. Then the third will be even smaller. This will be I0 by 61 and so on. See, so this is actually the contribution due to this term. And this is the contribution due to sine square alpha by alpha square term. And eventually, what are we going to see? We are going to see the superposition of these two effects. This effect plus this effect. And how will that look like? See, if I can draw an envelope or if I try to show that what is the trend of this, I hope all of you will agree with me that the trend can be drawn like this. So this is the trend. This is the trend for sine square alpha by alpha square term, whereas this is how the condition is. This, all the maximas are same, primary maximas are same, all the secondary maximas are same in this case. However, when these two superpose, as I was telling you, actually what is the seen picture or the intensity distribution? It now appears like this. Secondary, the first central maxima is the most intense one, as usual. But when I move to the first primary maxima, this intensity is less now. Again, the second primary maxima is having even less. And in between, I will have the secondary maximas. In the slower one, these are going to be even smaller. And as I'm going further, these will be having less and less intensity. So this is what we are going to see, and eventually, again, if I had to draw an envelope, what will I be seeing? I will again be seeing this kind of an envelope, which means the central maxima is the most intense. As I'm going to move forward away from the central maxima, the intensities will be smaller and smaller. And again, going back to the intensities of the secondary maxima, if this n is very large, here this picture that you all can see, remember, we have drawn this entirely on the basis that n is equal to only 5. Right, so we have had 3 secondary maximas, 4 minimas. However, when this n is very large, say n is equal to 500, what will be the effect? These secondary maximas will not even be visible to us on the screen. Alright, and we will only be seeing the spots which are caused due to the primary maximas only, and the central maxima will be the most intense. The first order primary maxima will be then the next intense. As we are going on increasing our order number of primary maximas, the intensities will be going on decreasing. So this is what is actually the diffraction effect due to n number of slits. Alright, so this actually completes our discussion and calculation about diffraction in n slits. Okay, the only thing which is left is to talk about grating, and these same things, how the grating will be reacting. And there are two actual topics which we have to talk about in case of a grating, which is one called the grating equation. Then we will also know something about the dispersive power of a grating, and we will also rather talk about the resolving power of a grating. That will be the last class that we will be having regarding the n slits. However, if you just consider n slits, today whatever we have done completes the entire discussion. What is left will be to talk about the grating only. Okay, so that is all for today's discussion. This is where we are going to end our discussion or calculation about n slits. And when considering n is equal to very large, that will take us to the next topic, which is the diffraction grating. Alright, so before I end today's class, just summarizing what all we have done. Today we have found out the condition for the secondary secondary maximas. We have also calculated the conditions for getting the minimas. Alright, after calculating the minima and the maxima conditions, we have also seen the intensity caused due to the secondary maximas. We have also calculated that, and then we have seen what is the intensity distribution for n slit looking like. So that's all for today and this class. I hope okay, there is a new student in our class today, Anshu, who is from Nepal. But Anshu, we do not talk about UPSC exams in this channel. UPSC is basically only for Indian residents. All right. So that's all for today. So in case we are having any further points that you want me to talk about it, please discuss. We can discuss it later. So that's all for today. Again, see you in the next class. Take care, all of you. Bye bye.